Right, hi. I'm a mechanical engineer, so you're probably wondering why is this mechanical engineer in this built environment sustainability conference? Well, we've investigated quite a number of tools for design and manufacture within our Innovative Manufacturing Research Centre. And what I'm going to tell you about today are some of the projects that we've carried out, where we've come from to get to where we are, and where we hope to go in the future, hopefully in 20 minutes, but there's lots of slides to get through. But you'll have an idea, hopefully, at the end of it, about why we see this as being relevant. And what I'd like you to do, for the academics in the audience, there may be certain aspects of our work that you see that you think, well, we can adapt that concept or that idea to fit into our research. And industrial people as well. You may say, well, here are some applications that we can maybe take forward into our particular environment. So, and you've heard a lot about BIM and 3D and so on. Maybe some of the tools that we've developed here can enhance that experience for people working in these environments. Okay, as I've said, I'm from the Innovative Manufacturing Research Centre. I, along with Mike Chandler, head up the Digital Tools Group, and this is really what we focus on in terms of our specialism. We're looking at human-centric tools, but particularly we're looking to work in the product design environment by applying virtual reality, signal processing, machine learning, biometrics, and psychology, believe it or not, to engineering processes. And within that, you can see that we're looking at these aspects here, particularly people-centered digital tools, with a view to capturing knowledge and rationale associated with engineering decisions. Okay, and we've had quite a bit of impact over the last 10 years of our IMRC, the funding for which finishes in March this year. So that's Mike's area, and we overlap greatly, and this is my area along with my colleague Theo Lim, and I'll talk about some of these projects shortly. In terms of digital engineering, well, I'll go through this route through the presentation very quickly and very briefly, and I'll tell you about some of our IMRC research first.
Edinburgh have collaborated with NCR.
This is where our work actually started, when we were looking at virtual reality applications to assembly. And within this environment, you can see that using a head-mounted display and a 3D mouse, we were able to take a virtual model. This was a printer assembly. There's the real assembly there, which was produced by NCR in Dundee. We're able to step through the build sequence for that. But the secret behind the method is to actually log in a time phase manner what the user is doing, because then we can pick up a chronological sequence, a build sequence associated with the product. And then from that build sequence, we were able to generate liaison charts and also assembly plans. And we passed those assembly plans onto the operators on the shop floor, and they were then able to build the product, not knowing where the plans had been generated. So we'd managed to generate an understandable English syntax assembly plan automatically without actually having the user typing in any information at all other than logging their build assembly sequence as they went through the virtual experience. We then took that a bit further and decided to look at a design problem, an electromechanical design problem, and that was in relation to cable harness design. And we developed a number of tools for actually immersing the user in the environment so we could scale up the model. It was automated teller machines. We were cabling up the modules within an automated teller machine. And what we were able to do was to design cable routes. And then we compared the virtual environment alongside CAD systems, traditional CAD systems, some of which you'll recognize there, in terms of performance. And what we found was that the more intuitive interface associated with using virtual reality in this way, because it was more ergonomically suitable to the way in which we work and we like to move, gave us substantial productivity gains over all the other CAD systems that we compared it against. So this was telling us there was something quite special about this kind of environment. The other thing I should mention is that in relation to those process plans that we were generating, what that also told us was that we were extracting knowledge associated with the process, because people could read the information and extract learning from it and then repeat the sequence. So it was an indirect way of actually acquiring knowledge. We then analyzed the design process for cable harnesses by taking the system a bit further and you can see some of the interfaces we're using there, much more improved over the previous example. And we're able to split down the design process and analyze the feasibility or usefulness of the interface itself. And we could see where the engineer was adding value to the product or wasting time, basically searching for information or taking breaks, trying to deal with the system interface. On top of that, we built in a cable harness assembly module as well, so we could actually, using these real-world standards, generate assembly plans associated automatically, again, with the cable harness, the bulkhead assembly, the cable assembly itself, and the installation. All timed, and this was the first time that this had been done using virtual environments as well. So, although we got all of these benefits, it was telling us two particularly important things, and we had a lot of firsts within there. We had a capability for non-intrusively analyzing engineering tasks, and we also had this important potential for knowledge acquisition. So our next project was to look at knowledge capture, and it was this kind of environment in which we're operating, whereby we would log a user in a time phase synchronous manner within a system, interpret the data and generate the data and put it into a knowledge store, and then if necessary try and prove if we could push that information at the expert engineer while they were using the system. And we managed to develop a lot of knowledge formats on the back of that, XML, and there's PSL, product specification language, which is an ontology whereby you can cross-analyze tasks. But even better, we were able to take both of these formats and create English syntax, explaining the process that the engineer had gone through. And this text show format is very important. And one example of this is that we could then embed these within a design rationale editor. This was developed by the Engineering Design Centre at Cambridge and used at Rolls-Royce, and it had to be updated manually as engineers stepped through a design process, but we could extract information or knowledge from the engineering process and populate this automatically. So it was a big advancement on the system. We could also produce integrated definition charts as well, flow charts of the engineering process, the design process or an assembly process. As well as this, we're able to show how we could push and actually capture information from engineers. Here you could see the engineer going to move a cable harness. They're given a list of options which we determined from the industrial partners, which were common things that they had to look out for when they were designing, and then the reason for it, and it was embedded within the description of the design change, again, done automatically. So it's a very fast way of generating these kind of data. We then moved on to haptic virtual reality. That's where you're helping the sense of touch associated with a virtual experience. Using phantom desktop devices, we're able to look at things like peg-in-the-hole experiments and placement, and show how by using more enhanced forms of haptics combined with visual experience, we could get more accurate placement and quicker placement in terms of potential assembly problems. And even adding in chamfers to virtual products speeded up the process. So we're getting the same benefits in the virtual world as we did in the real world. And we got very good responses associated with that. We also looked at assembly planning, again using haptics, and we were able to ergonomically analyze it using time and motion study methods based on those developed by Gilbreth, and generated chronocycle graphs for assembly sequences, so we could visualize build states at any scale, very small and very large, and also generate assembly plans with times against them as well, according to standards for the different kinds of moves that we make. And these were real-world assembly plan times, not virtual world. So we had all these opportunities presented to us after carrying out this particular research. And our vision was actually to look at very broad aspects of knowledge capture, and by this time we'd managed to demonstrate information push, English syntax capture, and all these different forms of knowledge representation, including storyboards describing in detail a process, and annotated video clips. So we could take the English syntax. Because it was time synchronized, we could put the description of what was happening in the video at each stage. And you could also embed that within a product lifecycle management system if you wished. We then did mechanical engineering task analysis, and this is a strange project. You probably say, why is he telling me about this? But what we did was, using a lot of partners, we decided to look at engineering knowledge acquisition through analysing the engineer. Now, these are other projects that we're doing. I won't have time to cover them here. But this is taking our original model, and where we've changed it is we're actually physically logging the engineer. We're measuring the engineer. We're measuring their brainwaves, we're measuring their responsive state, trying to classify their emotions as they're experiencing an engineering activity. And using EEG and ECG and EMG as well, it's possible for us to actually use a fuzzy model to go through a process whereby we can classify an engineer's emotions as they're carrying out a design activity. And using the Nexus and EEG cap, we're able to, and our synchronous architecture, which looks at keyboard strokes, it looks at inputs from data in terms of the CAD system, it looks at document access, and so on. We integrate all those in a time-phased manner so that we can look at the data across the whole design process activity. And I'll step through this at the moment. We're looking at alpha waves within our system, and what we're able to do is map the physiological signals onto the arousal and valence space of the user. I'm happy to go through this in a lot more detail if anybody wants to ask questions later on. And then we're able to map the arousal and valence space onto the emotions of the user via effect grids. And what this means is that these are effect grids that allow us looking at arousal and valence, positive and negative, and we can identify these partners through our biophysical monitoring. And what we're able to do is, looking at all these different areas in which we could classify these emotions, it's possible for us to go through a fuzzy logic model and determine these spaces associated with, for example, galvanic skin resistance and EEG in terms of arousal and valence, and then extend the fuzzy model to look at the relationships associated with emotions to give us these activity grids in a surface graph form, which we could then analyze and produce emotional states for the user going through a sequential activity. And here you can see there's frustration, engagement, satisfaction, and challenge. As they were going through designing a little car, you can see the frustration was very low here and they were satisfied, they weren't feeling much of a challenge, and there's the engagement, that was pretty low as well, but as soon as they hit a problem, the frustration went up, satisfaction started to go down, the engagement increased, and the challenge started to increase as well. And you can see that continuously challenging, going up as they ran out of time. So it was giving us a new way of looking at how people are performing in digital engineering environments. And I suppose the biggest surprise of all was that we detected that engineers actually have emotions. Yeah? Okay, so, and looking at the experimental setup, we also used it in a game activity because we're looking at games interfaces for CAD packages. And in the design of a bracket, we're looking at game interfaces, trying to see if game interfaces improve the experience of the user as they go through a design. But that's another area that will be, I've not got time to cover. However, you can see as well, we can get an English syntax description of the process that the engineer has gone through, and also we could do the IDEF diagrams and the DREAD diagrams, design rationale diagrams, as before, using a CAD system. Okay, this wasn't using VR, this is using CAD system. So we could use these tools in any environment. There's a DREAD diagram there. And we can also map the emotions against the actual process that they've gone through too. And we're now looking for connections whereby we've deliberately designed decision-making points within these sequences so that we can see if we get certain combinations of emotion that say to us, this is a design taking place here. So we can capture that without the engineer having to tell us. But we've a lot of work to do before we can get to that stage, and probably have to classify a lot more emotions and measure a lot more in relation to their physical experience. Okay, so we've got further experimental work to do. We've now got a portable system. We've taken to a few companies like Celex. We've taken it to BA Systems and so on, and got some results of experienced engineers, and we're analysing those as well. In terms of new projects, well, we've looked, the one we've been doing the last year is probably the most relevant to this conference. It's virtual aided design engineering reviews. And the idea is to automatically and unobtrusively capture and review knowledge. Now, we've looked at all those knowledge formats, but what about groups of people working together and trying to extract their intent associated with with a design? And also, how can we access that quickly? So the idea was triggered because we went to all these partners and found that they were actually struggling to review large engineering projects and formalize the information and then make it accessible afterwards. So what we did was we developed an architecture whereby you can go in our virtual reality wall system and you can annotate the models. And as you annotate the models, and remember our synchronous time-phased architecture is running in the background all the time, as you annotate the models, you make links with discussions that are going on, with documents that you're accessing, with video as well, and any other inputs that are being provided during the design review process. So you've got a team of people sitting around a table, interacting with a virtual model and annotating it. So it's an extension, if you like, to a lot of what you've seen already. And what you can do is, because you've got this structure here, in terms of maybe the BIM, or a product lifecycle management system, as we would say in mechanical engineering, you can actually put all these annotations against a part number, or a sub-assembly number, or an assembly. And these are the same keys that are used, or a description of a product or a part. The same kind of keys that are used, data that are used to link information together in a PLM or a BIM system. And then, if we're capturing these in a time-phased manner and linking them and tying them against the part numbers, it means that we can produce outputs that can be fed into a PLM system or a BIM system, and actually you can access in a very fast way information associated with design changes. Okay, so here's some of our colleagues from Skanska looking at probably the Carstairs design, I think, services design in our system. There you can see them actually sitting around the table. We've had about 5 or 6 companies in now using the system to give us feedback with regard to how it operates. And then as they go through, they're able to annotate and update either by typing in or speaking in what the various modifications are that they want to carry out associated with the product. And remember, this is all linked together and being tied up in an integrated database, which hopefully can be reused. Here's an example of one of the boxes in one of the design reviews. You've got action buttons here, and you've got various kinds of activity that you could post against a particular annotation so that you can classify them, and these are all captured as well. And what this means is that you've got the annotations associated with the geometry, you've got the discussion, and you've got all these other inputs, all time-phased, so that you can search through them and see cause and effect relationships during the design review. And there are some of the flags that we use, just as a bit more detail. We can attach documents. And what we want to eventually do is get rid of this and do everything through audio and convert the audio into text form so we can analyze it later on and produce other kinds of format. This is the kind of table that's produced at the end. You can see it's in part number form, but we can put it in chronological order as well in terms of activity. And what the user can do, and this is the sort of temporal data, the timeline associated with the activity, you can see that we've got these blocks here which relate to audio recordings. We've got these lines that relate to where annotations were added, and then by clicking on here against a part number, we can actually replay the discussion associated with that particular design change. So it gives us a very powerful way of actually revisiting engineering data and engineering knowledge in a way that we haven't been able to do before. And that's just the start. This is just a platform, and what we'd like to do is basically take some of those tools, these design tools that we showed you earlier on, and embed them in this system as well, so that we can do assembly, so that we can add and update the design as well. This is just our base system, which we know can actually provide a good solution in terms of long-term knowledge capture and access for industry. So we've got a base system that's applicable, but it's a foundation on which we could do lots more engineering knowledge capture and reuse research. Okay, so in the future, these were 2 conferences that we visited and chaired, and these were the issues that came out of the conferences in terms of virtual reality, and these were the projects that we were already doing in relation to engineering. So we're obviously getting the direction right for a discrete product manufacture. This was our vision way back in 1992 about how we felt the future world would look for engineers in 20 to 30 years' time, And I think with a lot of the tools that are now in the market and the tools that we're developing, we're moving towards this kind of globalized virtual concurrent engineering environment. Our dream is to have all these knowledge capture techniques, not just at the design stage, but all the way through the product life cycle, feeding into an accessible knowledge store, accessible so that not only can we see, for example, in 20 years' time, why a decision was made on a particular building and why a structure was designed in the way it was, and we better not modify that during our refurbishment, but also in terms of young engineers, trainee engineers, going into databases like this and learning from the experienced people, because one of the biggest problems we have as engineers or architects is knowledge loss when people retire or leave the company. With systems like this, we have the capability to capture that rationale and store it for a very, very long time in a structured and reusable way. And if any of you want to talk about projects, we're quite happy to have a discussion with you, whether it's academic colleagues, as I say, or industrial partners who think they can take some of these concepts further. Okay, I'll finish there. Thank you.